What if we're not alone? For centuries, humanity has gazed at the stars, wondering if other worlds might harbor life, and now we're closer than ever to finding the answer. Astronomers have discovered thousands of planets beyond our solar system, each one a tantalizing mystery. Some orbit their stars in just the right zone, where temperatures could allow liquid water and perhaps life as we know it to exist. These distant worlds, some eerily similar to Earth, others fantastically alien, have transformed our cosmic neighborhood from a collection of specks into a playground of possibilities. Think about that for a moment. In the vast ocean of space, we've pinpointed islands where life might have taken root. Some of these planets are bathed in perpetual twilight, their skies painted in hues we can barely imagine. Others are lashed by supersonic winds or locked in eternal embrace with their suns. Yet, against all odds, they could be home to something extraordinary. The very idea sends shivers down the spine, because if life exists out there, it means the universe is far more vibrant, far more mysterious than we ever dared to dream. Today, we're setting off on a journey to explore 25 of the most promising alien worlds that could harbor life. From frozen ocean moons to super-Earth shrouded in thick, steamy atmospheres, each of these destinations holds clues to one of humanity's oldest questions. Some are familiar, like the much-discussed Proxima b, right in our cosmic backyard. Others lurk in distant star systems, defying our expectations at every turn. Together, we'll uncover their secrets, weigh their chances of hosting life, and maybe, just maybe, catch a glimpse of what could be waiting among the stars. So buckle up, the hunt for our cosmic neighbors starts now. Proxima Centauri b isn't just any exoplanet, it's our next-door neighbor in the cosmos, orbiting the closest star to our Sun. A mere 4.2 light-years away, this rocky world sits snugly within its star's habitable zone, where temperatures might allow liquid water to pool on its surface. Picture an Earth-sized planet basking in the crimson glow of Proxima Centauri, a red dwarf far cooler and fainter than our Sun, but don't let its cozy position fool you. This world is a land of extremes. Tidal locking means one side is forever scorched by daylight, while the other languishes in eternal night. A perpetual twilight ribbon between these two realms could offer just the right conditions for life to cling on. Then there's the star itself, a temperamental toddler prone to violent outbursts. Proxima Centauri unleashes monstrous flares, bombarding its planets with radiation that could strip away atmospheres and scald surfaces. Yet life on Earth has proven resilient in the harshest environments, from boiling hydrothermal vents to frozen tundras. Could similar tenacity exist here? Some scientists speculate that a thick atmosphere or global ocean might shield Proxima b's surface, while underground habitats could offer refuge from the stellar tantrums above. What truly excites researchers is the tantalizing possibility of detecting signs of life in our lifetime. Proxima b's proximity makes it a prime target for next-generation telescopes, which could one day analyze the chemistry of its atmosphere for fingerprints of biological activity. Imagine the revelation if we found hints of oxygen, methane, or even industrial pollutants, evidence that we're not the only ones looking up at the stars, wondering who else is out there. For now, Proxima Centauri b stands as a beacon of hope, a world close enough to study in detail, yet mysterious enough to keep us dreaming. The hunt for life on Proxima Centauri b isn't just theoretical. Scientists are already devising ingenious ways to peel back its secrets. At the cutting edge is Breakthrough Starshot, an ambitious project that sounds more like science fiction than reality. Imagine swarms of tiny spacecraft, each no larger than a postage stamp, propelled by Earth-based lasers at a fifth the speed of light. These featherweight probes could reach Proxima b in just 20 years, snapping photos as they zip past its crimson skies, but the challenges are staggering. These nanocraft must survive decades of interstellar radiation, avoid collisions with space dust, and somehow transmit data across the vast gulf back to Earth. Even a single grain of sand could vaporize them on impact. While Starshot captures imaginations, other missions take a more measured approach. Next-generation telescopes like the extremely large telescope now rising in Chile's Atacama Desert could analyze Proxima B's atmosphere from right here in our solar system. By capturing the faint starlight filtering through its air, if it has any, scientists could hunt for chemical fingerprints of life. Oxygen and methane swirling together would spark excitement, since these gases quickly destroy each other unless constantly replenished, possibly by living organisms. But red dwarf stars complicate the picture. Their frequent flares can rip away atmospheres entirely or create false positives, oxygen produced by stellar radiation rather than photosynthesis. The ultimate dream, detecting industrial pollutants like chlorofluorocarbons, which would signal not just life but intelligent civilization. Current instruments aren't sensitive enough to confirm such subtle traces, but upcoming space telescopes like the Habitable Worlds Observatory aim to change that. Picture this: in 15 years, we might have spectral data revealing whether Proxima B's atmosphere contains water vapor, carbon dioxide, or even the telltale haze of smog. Every flicker of light from that distant world could rewrite our place in the universe. Until then, Proxima Centauri b remains both the most accessible and most frustrating target, close enough to spark bold missions, yet still shrouded in enough mystery to keep us questioning what twilight creatures might stir beneath its crimson sun. TRAPPIST-1e isn't just another exoplanet, it's part of one of the most extraordinary planetary systems we've ever discovered. Nestled in the habitable zone of its ultra-cool dwarf star, this Earth-sized world is one of 7 siblings locked in a delicate cosmic dance. Imagine a solar system so compact that all its planets could fit within the orbit of Mercury, their years shorter than an Earth week. Yet despite this closeness, TRAPPIST-1e might just have the perfect ingredients for life. Its rocky surface and potential for a thick atmosphere place it high on the list of worlds that could harbor living organisms. What makes TRAPPIST-1e stand out isn't just its Earth-like size, it's the way it interacts with its stellar family. The planets in this system are so close together that if you stood on one, others might loom large in the sky, their surfaces visible to the naked eye. But this proximity comes with challenges. The gravitational tugs between planets could generate intense tidal heating, turning their interiors into molten furnaces. Or if TRAPPIST-1e has managed to hold onto its atmosphere, those same forces might create a stable climate, with gentle temperature swings ideal for liquid water. The possibilities are as tantalizing as they are uncertain. Enter the James Webb Space Telescope, our most powerful eye on the cosmos. JWST has already begun probing TRAPPIST-1e's atmosphere, hunting for traces of carbon dioxide, water vapor, or even methane, chemical clues that could hint at biological activity. Early observations suggest this world might be a water-rich paradise, its surface draped in global oceans. Alternatively, it could be a steamy greenhouse, its skies choked with thick clouds. But the real excitement lies in what we haven't found yet. If JWST detects an unexpected mix of gases like oxygen alongside methane, it could be the strongest hint yet that we're not alone in the universe. The beauty of TRAPPIST-1e is its mystery. It challenges everything we thought we knew about planetary systems, proving that life could thrive in the most unexpected places. Whether it's a water world, a volcanic wasteland, or something entirely alien, this planet represents the next frontier in our search for cosmic neighbors. And with JWST peeling back its secrets one wavelength at a time, we might not have to wait long for answers. The TRAPPIST-1 system isn't just about its crown jewel. This cosmic family of 7 rocky planets offers a fascinating laboratory for how life might spread among neighboring worlds. Take TRAPPIST-1f and g, siblings that straddle the outer edge of the habitable zone. While 1F might be a frozen snowball, 1G could enjoy temperate conditions with the right atmospheric blanket. But here's where it gets intriguing. Their tight orbits, some closer than Mercury is to our Sun, raise the possibility of panspermia, the natural spread of life between planets. Imagine meteorites chipped off one world by asteroid impacts, carrying microbial hitchhickers that rain down on another millions of years later. In our solar system, Mars and Earth likely exchanged rocks this way, but TRAPPIST-1's intimate setup could turn this process into a planetary conveyor belt. What makes this system so extraordinary is its compact architecture. The planets are so close that if you stood on TRAPPIST-1e, its siblings would dominate the skyline, some appearing larger than our Moon. Their gravitational interplay creates tidal forces far stronger than Earth experiences, potentially heating their interiors through friction. This could sustain subsurface oceans on frozen worlds like 1H, hidden beneath miles of ice. Even more striking is the shared stellar environment. The system's calm red dwarf star, far less volatile than Proxima Centauri, bathes all 7 planets in similar ultraviolet light and radiation. If life evolved on one world, its chemical building blocks might find familiar conditions next door, yet challenges abound. The same gravitational dance that could nurture life might also trigger extreme volcanism or strip away atmospheres over time. TRAPPIST-1F, for instance, could either be an icy wasteland or a water-rich world with a thick greenhouse atmosphere keeping it warm. Meanwhile, 1G's position at the habitable zone's outer edge makes it a prime candidate for a global ocean if it retained enough internal heat to avoid freezing solid. The James Webb Space Telescope has already begun decoding these possibilities, analyzing atmospheric clues across multiple planets simultaneously, a first in exoplanet science. The real revelation here is the diversity of habitable scenarios packed into one miniature system. Unlike our solar system's spread-out planets, TRAPPIST-1's worlds could share not just ingredients for life, but potentially life itself. Whether through meteorite exchanges or parallel evolution under similar conditions, this cosmic neighborhood suggests that where one habitable world exists, others might follow. As we continue peering into this planetary mosaic, each new discovery reminds us, life may not be a solitary accident, but a shared phenomenon woven into the fabric of the universe. Kepler 186f changed the game when astronomers spotted it in 2014, the first Earth-sized world ever found orbiting comfortably within another star's habitable zone. Picture a planet only 10% larger than our own, circling a dim red dwarf star 500 light-years away. Its discovery shattered assumptions, proving that planets like ours weren't just theoretical, they were out there waiting to be found. But this world is no Earth twin. Its crimson sun, barely a fifth the size of ours, bathes the planet in a perpetual sunset glow, with light levels more akin to twilight on Earth an hour before sunset. What makes Kepler 186f so intriguing is its delicate balancing act. Nestled at the outer edge of its star's habitable zone, it completes an orbit every 130 Earth days. At that distance, liquid water could exist if the planet has a thick enough atmosphere to trap heat, but red dwarfs are notorious for their violent youth. Early in their lives, these stars erupt with radiation that might have stripped away any protective gases, leaving Kepler 186f a barren rock. Yet if it held onto an atmosphere or later developed one through volcanic activity, it could host vast oceans beneath skies tinged permanent red. The challenges don't end there. Tidal forces from its star may have locked one face of the planet in eternal daylight, the other in endless night. But that twilight strip along the terminator line where day meets night could offer a refuge with temperatures stable enough for water to pool. Scientists speculate about another possibility, a global ocean beneath an ice shell kept liquid by geothermal heat. Either scenario raises tantalizing questions. Could photosynthetic life exist under a dim sun, perhaps using infrared light? Or might chemosynthetic organisms thrive near hydrothermal vents as they do in Earth's deepest oceans? Kepler 186f's true legacy lies in what it represents. Before its discovery, we only knew of gas giants in habitable zones, planets where life, if it existed, would float in unearthly atmospheres. This rocky world proved the cosmos could craft places strangely familiar. Its detection paved the way for thousands of exoplanet discoveries, each expanding our understanding of where life might take root. While we may never know for certain what lies on its surface without advanced telescopes, Kepler 186f remains a milestone, a quiet reminder that Earth may be just one of many homes for life in the universe. LHS 1140b isn't just another exoplanet, it's a heavyweight contender in the search for life, a super-Earth that's captured scientists' attention for its rare combination of promising traits. Orbiting a quiet red dwarf star 49 light-years away, this world is nearly 7 times Earth's mass, yet it's not a gas giant. Instead, its density suggests a rocky composition, possibly wrapped in a thick atmosphere that could cling tightly to its surface. What makes this planet stand out isn't just its size, it's the remarkable stability of its star. Unlike the tantrum-throwing red dwarfs we've encountered elsewhere, LHS 1140 emits relatively gentle radiation, giving this super-Earth a fighting chance to hold onto its atmosphere over billions of years. Imagine a planet where the air is so dense that it acts like a thermal blanket, redistributing heat from its sunlit side to the eternal darkness of its opposite face. Tidal locking likely leaves one hemisphere perpetually bathed in dim crimson light, the other shrouded in cold. But that dense atmosphere could smooth out these extremes, creating twilight zones where temperatures hover in that Goldilocks range, neither too hot nor too cold for liquid water. Some models even suggest LHS 1140b might be a water world, its surface entirely submerged beneath a global ocean hundreds of miles deep. Under that immense pressure, exotic forms of ice could exist, not the familiar brittle sheets we know, but hot, dense phases like Ice 7, a substance that stays solid even at scorching temperatures. The real excitement lies in what's coming next. The James Webb Space Telescope has already set its sights on this enigmatic world, its infrared eyes probing for atmospheric clues. Scientists are hunting for the chemical fingerprints of water vapor, carbon dioxide, or even nitrogen, gases that could hint at Earth-like conditions. But the stakes are higher than ever. If JWST detects methane alongside oxygen, it would create a tantalizing puzzle. These gases react quickly and destroy each other unless continuously replenished, a process often linked to biological activity. Of course, geological processes could mimic these signatures, which is why researchers are also looking for more complex molecules like dimethyl sulfide, a compound on Earth produced almost exclusively by marine phytoplankton. What makes LHS 1140b so compelling is its potential to rewrite the rules of habitability. Most known super-Earths are either too hot or lack atmospheres altogether. But this world sits comfortably in its star's habitable zone while appearing to retain the gases crucial for life as we know it. Upcoming observations could reveal whether it's a steamy jungle planet, a frozen globe with subsurface oceans, or something entirely unexpected. One thing's certain, this isn't just another dot in the sky. It's a laboratory for testing our boldest ideas about where life might thrive. And with every new dataset, we inch closer to answering whether we're alone in the cosmos. Teegarden's star B doesn't shout for attention like some exoplanets, it whispers possibilities. Orbiting one of the quietest red dwarfs ever discovered, this unassuming world 12 light-years away holds a remarkable distinction, an Earth Similarity Index score of 0.95, placing it among the most Earth-like planets we've found. Picture a rocky world slightly heavier than ours, basking in the gentle glow of a star so faint it wasn't even spotted until 2003. Unlike the violent flares of Proxima Centauri, Tigodon's star hums along steadily, a cosmic elder offering its planets rare stability in the turbulent red dwarf family. The numbers tell a compelling story. Completing an orbit every 4.9 Earth days, Tigodon's star B nestles comfortably in its star's habitable zone where surface temperatures, if it has an Earth-like atmosphere, could average around 28 degrees Celsius. That's beach weather by terrestrial standards, but here's the twist. With a host star emitting less than 1% of our sun's visible light, daylight on this world would resemble a perpetual overcast evening. Photosynthetic life here wouldn't rely on bright sunshine but might adapt to harvest infrared radiation, painting alien forests in deep burgundies and blacks unseen on Earth. Tidal locking likely keeps one face forever turned toward its dim sun, creating extremes that could challenge life, yet models suggest atmospheric circulation might redistribute enough heat to prevent the dark side from freezing solid. Imagine a world where slow, powerful winds ferry warmth from day to night, creating a twilight ribbon hundreds of miles wide where temperatures hover in the liquid water sweet spot. Alternatively, a global ocean could serve as nature's climate control, its currents smoothing out temperature variations. The real magic lies in Tigodon's star itself. At 8 billion years old, nearly twice the Sun's age, this system has had ample time for life to emerge and evolve. While younger red dwarfs fry their planets with radiation during volatile early eons, Tigodon's tranquil nature means its planets might have retained or developed thick atmospheres. Recent studies hint at possible water clouds in Tigodon B's air, a tantalizing suggestion of active hydrology. Detecting signs of life here pushes our technology to the limit. The star's faintness makes atmospheric analysis brutally difficult, though next-generation telescopes like the Habitable Worlds Observatory could change that. Scientists dream of spotting oxygen or methane in its air, or perhaps more exotic biosignatures tailored to this unique environment. For now, Tigodon's star B remains a quiet enigma, a world that checks nearly every box for habitability, circling a star so discreet we didn't notice it until this century. In the cosmic silence between flares and fireworks, might the most promising home for alien life be the one nobody heard about until recently? K2-18b isn't just another exoplanet, it's a cosmic paradox wrapped in hydrogen and mystery. Discovered 120 light-years away in the constellation Leo, this super-Earth defies easy categorization. Larger than our planet but smaller than Neptune, it exists in that tantalizing gray zone where worlds could be rocky giants or steamy water planets. But what really sets K2-18b apart is its title as the first known hycean world, a theoretical class of planets with global oceans beneath thick hydrogen atmospheres. Picture an endless sea stretching to the horizon, its surface hidden under swirling pinkish haze, where the air isn't nitrogen and oxygen but lightweight hydrogen pressing down with incredible force. The excitement peaked in 2023 when the James Webb Space Telescope detected potential traces of dimethyl sulfide in K2-18b's atmosphere, a molecule on Earth produced almost exclusively by marine phytoplankton. That single finding sent ripples through the scientific community. Could this be our first whiff of alien biology? The reality is far more complex. While dimethyl sulfide excites astrobiologists, other explanations exist. Geological activity might produce similar signatures, or the data could be distorted by stellar interference. Even the planet's temperature is a puzzle. Orbiting a cool red dwarf, K2-18b receives similar stellar radiation to Earth, but its hydrogen blanket might trap heat so effectively that surface waters boil, creating a pressurized steam bath rather than a life-friendly ocean. Debates rage about whether hycean worlds can truly host life. Their extreme pressures, hundreds of times greater than Earth's surface, would crush familiar organisms. Yet in our own oceans, creatures thrive near hydrothermal vents under crushing weights. The real question is whether chemistry could spark life in such alien seas. Hydrogen-rich atmospheres might react with water to form prebiotic molecules, the building blocks of biology. Alternatively, tidal forces could keep subsurface oceans liquid beneath ice shells, hiding ecosystems entirely unlike anything we know. Future observations aim to settle these controversies. Webb's follow-up studies will check if the dimethyl sulfide signal holds or fades, a cautionary tale in how early data can tantalize before confounding. Meanwhile, astronomers are developing new tools to distinguish true biosignatures from false positives. K2-18b stands as both a beacon of possibility and a lesson in cosmic humility, reminding us that the most promising worlds often guard their secrets fiercely. Whether it's a biological oasis or a fascinating dead end, this hycean world has already expanded our imagination of where life might take root. Hycean worlds rewrite the rules of where life might exist. These hypothetical planets, first proposed in 2021, blend characteristics of gas giants and water worlds, global oceans capped by thick hydrogen atmospheres, creating environments unlike anything in our solar system. The traditional habitable zone concept, built around Earth-like conditions, struggles to contain them. K2-18b proves that life, if it exists there, could thrive under pressures that would flatten terrestrial organisms, in seas warmed not by sunlight penetrating deep waters but by atmospheric compression and geothermal vents below. What makes hycean worlds so revolutionary is their sheer versatility. Planets like K2-18b often orbit outside classical habitable zones, yet their insulating hydrogen blankets might trap enough heat to maintain liquid water where conventional models predict only ice. Consider TOI 270d, another hycean candidate discovered in 2023. This Neptune-sized world orbits so close to its star that surface temperatures should vaporize water, yet its immense atmospheric pressure could create a stable supercritical ocean where liquid and gas phases blur into one. Here, the very definition of surface becomes ambiguous. Life might float in nutrient-rich layers between crushing depths and scorching upper hazes. The challenges for potential organisms are staggering. Hydrogen-rich atmospheres lack free oxygen, forcing life to rely on alternative metabolisms, perhaps harvesting chemical energy from water-rock interactions or atmospheric compounds. But extremophiles on Earth have already demonstrated such adaptability, thriving in acidic hot springs or oxygen-starved mud. Hycean worlds also present detection hurdles. Their hazy atmospheres obscure surface details, while complex atmospheric chemistry can mimic biological signatures. When JWST spotted potential dimethyl sulfide on K2-18b, it wasn't just hinting at life, it revealed how easily abiotic processes could impersonate it. Yet the allure persists because hycean planets vastly expand the cosmic real estate where life could emerge. Red dwarfs, making up 75% of Milky Way stars, frequently host such worlds. Their formation process, rocky cores accreting primordial hydrogen before their stars ignited, might be more common than Earth-like planet formation. If even a fraction of hycean worlds develop life, the galaxy could teem with organisms as alien as their environments. K2-18b and TOI 270d are just the first glimpses of this possibility, proving that the universe's creativity outpaces our terrestrial imaginations. The search now shifts from merely finding habitable zone planets to understanding atmospheric dynamics that could sustain liquid water in unexpected places. Future telescopes will hunt for hycean worlds with clearer biosignatures, perhaps methane ratios or complex molecules that defy geological explanation. Every new discovery in this category forces us to reconsider not just where life might exist, but what forms it could take when born under pink hydrogen skies instead of blue nitrogen ones. In that sense, these worlds aren't just scientific targets, they're mirrors reflecting back how little we truly know about life's potential. GJ357d isn't another face in the exoplanet crowd, it's a heavyweight champion of possibilities. Discovered 31 light-years away in the constellation Hydra, this super-Earth tips the scales at over 6 times our planet's mass, yet its true nature remains one of astronomy's most tantalizing puzzles. What sets it apart is its orbit, a leisurely 55 Earth-day journey around a placid red dwarf star, placing it squarely in the habitable zone where liquid water could pool on its surface. But here's the twist: depending on its atmosphere, GJ357d could be either a balmy paradise or a frozen wasteland. Imagine a world where the air itself holds the key to its habitability. Without an atmosphere, surface temperatures would plummet to -53°C, inhospitable to life as we know it. But if this super-Earth has retained a thick blanket of greenhouse gases like carbon dioxide, something extraordinary happens. Models suggest its skies could trap enough heat to push temperatures above freezing, creating conditions where rivers might flow and lakes could persist. The numbers tell a compelling story. With just 1/10 the sunlight Earth receives, GJ357d's potential warmth hinges entirely on atmospheric chemistry. It's a reminder of how delicate the balance is between a frozen rock and a living world. The challenges of studying GJ357d are as immense as its mysteries. Current telescopes struggle to analyze its atmosphere directly. Its dim red dwarf star outshines it by thousands of times, drowning out the faint whispers of light filtering through its air. But future instruments like the Habitable Worlds Observatory could change everything. Designed to block stellar glare with advanced coronagraphs, these next-generation telescopes might finally reveal whether GJ357d possesses water vapor, carbon dioxide, or even methane gases that could rewrite our understanding of habitable worlds. What makes this planet so captivating isn't just its potential for liquid water, it's the way it defies expectations. Most known super-Earths orbit so close to their stars that they're roasted into barrenness, but GJ357d's wide orbit offers a rare, stable environment. Some scientists speculate it could be a water world, its surface entirely submerged beneath global oceans. Others envision towering ice caps surrounding temperate equatorial bands where life might eke out an existence. The truth remains locked in light years of distance, waiting for technology to catch up to our curiosity. The deeper lesson here is one of cosmic diversity. GJ357d proves that habitable conditions can emerge in unexpected places around faint stars, on massive planets, under skies utterly unlike our own. As we continue refining our search for life beyond Earth, worlds like this remind us that the universe rarely follows our assumptions. Every new discovery peels back another layer of possibility, revealing just how inventive planetary systems can be. Whether GJ357d harbors life or stands as a monument to nature's variety, it's already expanded the horizons of where we dare to look. Wolf 1061c hovers dangerously close to the line between paradise and inferno. Just 13.8 light-years away, this rocky world orbits its dim red dwarf star so tightly that a full year passes in a mere 18 Earth days. That proximity places it right on the inner edge of the habitable zone, a razor's edge where the difference between a temperate climate and a runaway greenhouse effect comes down to atmospheric details we can't yet measure. Picture a planet caught in permanent embrace with its star, one hemisphere perpetually baked in crimson daylight while the other half lingers in eternal night. But Wolf 1061c's true drama lies beneath its surface, where tidal forces may be stirring a planetary furnace. The same gravitational pull that creates Earth's ocean tides could be wreaking far more violent havoc here. As the planet orbits, its star's uneven tug squeezes and stretches the interior, generating friction that might melt rock into magma on a planetary scale. On Jupiter's moon Io, similar forces produce the most volcanically active body in our solar system, a landscape constantly remade by erupting vents and rivers of lava. Wolf 1061c could be experiencing this phenomenon on steroids, its crust fractured by endless quakes and spewing enough heat to potentially sustain subsurface oceans. The paradox is striking, a world that's simultaneously being cooked from above by its star and churned from below by internal fires, yet the atmosphere holds the real key to its fate. If Wolf 1061c held onto substantial water during its formation, that moisture might now be fueling a thick, steamy shroud. Models suggest two terrifyingly plausible scenarios. The first mirrors Venus, trapped in a feedback loop where greenhouse gases boil away oceans, leaving behind a dead world shrouded in scorching carbon dioxide. But the alternative is breathtaking, a planet where dense clouds reflect just enough starlight to prevent overheating, creating stable conditions where water could persist in the twilight border between day and night. The wild card, Wolf 1061c's star isn't just dim, it's unpredictable. Red dwarfs often unleash powerful flares in their youth, and if this planet lost its protective magnetic field early on, those outbursts might have stripped its atmosphere entirely. Yet recent studies hint at a tantalizing possibility. Some super-Earths generate magnetic fields through the churning of molten metal in their mantles, not their cores. If Wolf 1061c's tidal heating keeps its interior partially molten, it could still deflect stellar radiation, sheltering any surviving atmosphere. What makes this world so compelling is its duality. At first glance, it ticks every box for a lifeless hellscape until you account for the creative ways nature might compensate. A thick atmosphere could redistribute heat to the dark side, while tidal forces might maintain underground reservoirs shielded from surface extremes. Future telescopes could settle the debate by hunting for chemical signatures like sulfur dioxide, a volcanic marker, or water vapor in its air. Until then, Wolf 1061c stands as a cosmic test case, challenging us to reconsider where life might cling on in environments we'd once written off as hopeless. Whether it's a cautionary tale or a beacon of adaptability remains one of the most electrifying questions in exoplanet science. Kepler 442b doesn't just rank high on the habitability scale, it redefines what we consider Earth-like. Orbiting a star 1,100 light-years away, this world stands out for striking a nearly perfect balance between size, temperature, and composition. At 1.3 times Earth's mass, it's large enough to retain a substantial atmosphere yet small enough to avoid becoming a gas-shrouded mini-Neptune. But the real magic lies in its stellar flux, the amount of energy it receives from its orange dwarf sun. Kepler 442b basks in about 70% of the sunlight Earth enjoys, putting it comfortably in the sweet spot where liquid water could exist without boiling away or freezing solid. What makes this exoplanet particularly compelling isn't just its present conditions, but its history. At 6 billion years old, it's roughly 1.5 times Earth's age, a detail that transforms it from just another habitable zone candidate into a prime target for complex life. Consider what that extra time represents. On our planet, single-celled organisms appeared within 1 billion years, but multicellular life took nearly 3 billion more to emerge. Kepler 442b has had an additional 2 billion years for evolution to work its miracles. Imagine ecosystems shaped by epochs longer than Earth's entire Phanerozoic eon, time enough for intelligence to arise, civilizations to bloom, and perhaps even transcend biology itself. The planet's star adds another layer of promise. Unlike the flaring red dwarfs that threaten many exoplanets, Kepler 442's sun is stable, emitting steady light with minimal harmful radiation. This orange dwarf is also metal-rich, meaning it formed with ample heavy elements to seed rocky planets. Spectroscopy suggests the exoplanet likely has a dense iron core like Earth's, possibly generating a protective magnetic field to shield its surface from cosmic rays. Combine these traits, and you've got a world where photosynthesis could thrive under amber skies, where continents might host forests adapted to gentler sunlight through broader leaves or darker pigments. Yet challenges persist. Tidal locking could leave one hemisphere scorched and the other frozen, though atmospheric circulation might mitigate extremes. The planet's greater mass means stronger gravity, potentially making flight harder for creatures, but also compressing its air into a thicker, more insulating blanket. Most tantalizing is the unanswered question of water. Current telescopes can't confirm if Kepler 442b has oceans, but its position and composition make it one of the best bets we've found. Kepler 442b represents more than just a potentially habitable world. It's a glimpse into how planetary systems mature given enough time. While Earth's story is still unfolding, this ancient planet might already hold the answers to whether life inevitably grows complex or if we're an extraordinary fluke. Future telescopes could analyze its atmosphere for biosignatures like oxygen or technosignatures from advanced civilizations. Until then, it remains a beacon in the cosmic dark, reminding us that some worlds aren't just habitable, they've had every opportunity to become something extraordinary. TOI 700d isn't just another exoplanet, it's a cosmic jackpot discovered by NASA, a planet-hunting test mission, and it checks nearly every box astronomers dream of. Located 100 light-years away in the constellation Dorado, this Earth-sized world orbits a small, calm red dwarf star, right in the middle of the habitable zone where liquid water could exist. But what truly sets it apart is its rarity. Of the thousands of planets TESS has identified, TOI 700d remains one of the few Earth-sized worlds found in this Goldilocks region around a non-flaring star. That alone makes it a prime candidate in the search for life, a needle in the cosmic haystack worth examining thread by thread. Picture a planet forever locked in an embrace with its star, one side bathed in perpetual daylight, the other shrouded in endless night. Tidal forces have likely slowed TOI 700d's rotation until it presents the same face to its sun at all times, creating extreme contrasts. The day side might simmer under a constant crimson glow, while the night side plunges into frigid darkness. Yet between these two extremes lies the Terminator line, a twilight belt where temperatures could hover in that delicate range where water stays liquid. If this world has managed to hold onto an atmosphere, winds might ferry warmth from the hot side to the cold, smoothing out the brutal temperature divide and creating narrow habitable bands. The real excitement, however, lies in what NASA models suggest. Climate simulations paint three vivid scenarios for TOI 700d. One depicts a water-rich world shrouded in thick clouds, its surface entirely covered by a global ocean. Another shows a dry, desert-like planet with minimal water, its atmosphere dominated by land masses and sprawling dunes, the most intriguing possibility. A hybrid world where vast oceans coexist with continents, much like Earth, but with weather patterns utterly alien, storms raging perpetually along the Terminator line where hot and cold air clash. Each scenario hinges on the planet's atmosphere, something the James Webb Space Telescope could soon unravel by analyzing the starlight filtering through its skies. What makes TOI 700d so valuable is its star's tranquility. Unlike the violent flares of Proxima Centauri or TRAPPIST 1, this red dwarf is remarkably stable, emitting minimal radiation that could strip away atmospheres over time. That stability gives TOI 700d a fighting chance to retain the very gases that might nurture life. Scientists are particularly eager to hunt for carbon dioxide, methane, or water vapor, chemical fingerprints that could hint at geological activity or even biology. The absence of an atmosphere would be equally revealing, teaching us about the survival odds for planets around even the calmest red dwarfs. The coming years could transform TOI 700d from a blur in telescope data to a world with known weather, chemistry, and perhaps even surface features. As JWST and future observatories turn their gaze toward this system, every new dataset will test our assumptions about habitable worlds. Whether it's a waterlogged globe, a windswept desert, or something entirely unexpected, TOI 700d represents more than just scientific curiosity. It's a benchmark for how Earth-like planets behave under alien suns. And in that role, it might just redefine what we consider a hospitable world. JJ 667cc sounds like something straight out of science fiction, a super-Earth bathed in the glow of not one but 3 suns. 23 light-years away in the constellation Scorpius, this planet orbits the smallest star in a triple system, a setup that paints its skies with an ever-changing celestial ballet. Imagine sunrises where multiple orbs climb above the horizon, casting overlapping shadows and shifting hues across alien landscapes. But beneath this stellar spectacle lies a pressing question. Could this world, with its complex gravitational dance and uncertain atmosphere, truly harbor life? Initial discoveries in 2012 sent shockwaves through the astronomy community. JJ 667cc's orbit placed it squarely in the habitable zone of its cool red dwarf host, JJ 667c. Early estimates suggested surface temperatures might hover around Earth-like averages, assuming it possessed an atmosphere similar to ours. The planet's mass, roughly 4 times Earth's, hinted at a rocky composition with enough gravity to hold onto substantial air and water. For a brief moment, it seemed we'd struck gold, a potentially habitable world right in our cosmic neighborhood. But the devil, as always, was in the details. Later studies revealed complications that tempered the early excitement. The other 2 stars in the system, JJ 667 A and B, orbit much farther out, yet their gravitational influence could destabilize the planet over long timescales. More critically, red dwarfs like JJ 667c emit most of their radiation as infrared light, which interacts differently with planetary atmospheres than our Sun's visible spectrum. For JJ 667cc to maintain liquid water, it would need a very specific atmospheric composition thick with greenhouse gases like carbon dioxide to trap heat, but not so thick as to trigger a runaway greenhouse effect like Venus. Then there's the tidal locking problem. Like many planets orbiting red dwarfs, JJ 667cc likely keeps one face permanently turned toward its star. Without atmospheric circulation to redistribute heat, the day side might bake under unrelenting infrared glare while the night side plunges into deep freeze. But nature often defies our simplest models. Some simulations suggest that dense atmospheres could transfer enough warmth to the dark side to prevent total freezing, creating a narrow habitable strip along the twilight zone where temperatures might allow liquid water. Alternatively, subsurface oceans heated by geothermal activity could thrive beneath icy shells, shielded from the harsh conditions above. The greatest controversy, however, revolves around the planet's very existence. Early radial velocity data suggested JJ 667cc might not be a planet at all, but a misinterpreted signal from stellar activity. While subsequent analyses have largely supported its planetary status, the debate highlights the challenges of detecting subtle wobbles in small, turbulent stars. Even today, some astronomers argue the system's complex dynamics could be masking the truth. What makes JJ 667cc so compelling isn't just the science, it's the philosophical implications. Here's a world that forces us to rethink habitability in chaotic environments. Triple star systems were once considered too unstable for life, yet JJ 667cc persists, challenging our assumptions. Future telescopes might one day analyze its atmosphere for biosignatures, searching for chemical imbalances that hint at biology. Until then, this enigmatic planet remains a cosmic riddle, a reminder that the universe's most promising worlds often lie in the gray zones between certainty and mystery. Whether it's a life-bearing oasis or a cautionary tale about over-optimism, JJ667cc has already expanded our understanding of where life might or might not take root. HD 40307G shatters the red dwarf stereotype, a super-Earth orbiting a star strikingly similar to our Sun, a rare gem in the exoplanet catalogue. Located 42 light-years away in the constellation Pictor, this world weighs in at 7 times Earth's mass, yet what truly sets it apart is its orbit. Circling its Sun-like star at just the right distance, HD 40307G spends 197 Earth days in its Goldilocks year, neither too close to fry nor too far to freeze. Unlike the cramped orbits of most habitable zone planets around dim red dwarfs, this super-Earth enjoys room to breathe, with an orbital distance comparable to Mercury's but around a far gentler Sun. Seasonal rhythms could paint this world with stunning diversity. Earth's tilt gives us summer and winter, but HD 40307G might experience even more dramatic shifts. Some models suggest its axial tilt could be extreme, like a cosmic spinning top wobbling wildly as it orbits. Picture winters where entire hemispheres plunge into months-long darkness beneath veils of ice, followed by summers where midnight sun bathes continents in unending daylight. These oscillations wouldn't just affect temperatures, they could drive monstrous weather systems. Hurricanes the size of continents might rage across oceans, fueled by temperature differentials dwarfing anything on Earth. Or if the planet rotates quickly enough, Coriolis forces could twist winds into intricate global patterns, stitching jet streams through its skies like atmospheric lacework. The star itself presents both promise and puzzles. At roughly 70% the Sun's mass, HD 40307 emits a familiar spectrum of light, raising intriguing possibilities for photosynthesis. Alien plants here wouldn't need to adapt to the crimson glow of a red dwarf. They might bask in yellowish hues not unlike Earth's, potentially evolving leaf structures we'd recognize. Yet mysteries abound. The system contains at least 5 other planets, their gravitational nudges potentially destabilizing HD 40307G's climate over millennia. Moreover, the star's age nearing 6 billion years suggests this world has had ample time for life to emerge, but also for its atmosphere to thin under relentless stellar winds. Surface conditions hinge on a delicate balance. With 7 times Earth's gravity, HD 40307G could cling to an atmosphere denser than Venus's, pressing down with enough force to liquefy carbon dioxide into shallow seas. Alternatively, that same gravity might lock away water deep in mineral structures, leaving continents parched under hazy skies. The James Webb Space Telescope could soon settle these debates by analyzing atmospheric refraction during transit's subtle bending of starlight that reveals gas compositions. A detection of nitrogen-oxygen blends would electrify astrobiologists, hinting at Earth like air forged by biology. What makes this super-Earth extraordinary is its defiance of trends. Most known habitable zone planets orbit turbulent red dwarfs, but HD 40307G offers a glimpse of something rarer, a world where life might unfold under conditions eerily reminiscent of home. Whether it's a waterlogged giant with hypercanes scouring its surface or a continental paradise with seasons measured in centuries, this planet expands our imagination of where life could take root. In a cosmos dominated by red dwarfs, HD 40307G stands as a reminder. Sun-like stars might still host the most familiar alien worlds we'll ever find. Kepler 62f emerges from the Kepler mission data like a cosmic doppelganger, a world so eerily Earth-like in size and position that it sparked instant fascination. Orbiting a star 1,200 light-years away in the constellation Lyra, this exoplanet measures just 1.4 times Earth's diameter, placing it firmly in the sweet spot between puny Mars and bulky mini-Neptunes. But it's not just the tape measure that excites scientists. Kepler 6.2f's orbit traces a near-perfect path within its star's habitable zone, receiving about 41% of the stellar energy Earth gets from the Sun. That puts it in a Goldilocks scenario, potentially cool enough to avoid a runaway greenhouse effect, yet warm enough to prevent global glaciation. The real intrigue lies beneath its hypothetical skies. Climate models suggest two breathtaking possibilities. One paints Kepler 6.2f as an aquaplanet, its surface entirely shrouded by a global ocean hundreds of miles deep. In this scenario, the lack of continents would create currents unlike anything on Earth, with planet-spanning whirlpools redistributing heat between hemispheres. The other theory imagines a world of scattered archipelagos, where volcanic activity has punched through the water's skin to create island chains dotting shallow seas. Both versions depend critically on atmospheric composition. A thick carbon dioxide blanket could trap enough heat to maintain liquid water despite the star's faint glow, while thinner air might leave it an ice ball with isolated melt zones near the equator. Then there's the star itself, a dim orange dwarf barely 20% as luminous as our Sun. This presents both challenges and opportunities. On the downside, Kepler 6.2f orbits much closer than Earth to receive comparable warmth, completing a revolution every 267 days. Such proximity might trigger tidal locking, leaving one hemisphere perpetually sunlit and the other in endless night. Yet orange dwarfs offer surprising advantages over their red dwarf cousins. They're far more stable, with minimal flaring that could strip atmospheres over time, and they emit light across a broader spectrum, including visible wavelengths that could power photosynthesis. If plants exist here, they might appear black or deep purple to absorb every precious photon. Their leaves evolved to maximize energy capture under weak amber skies. The greatest mystery remains water. While Kepler 6.2f likely formed beyond the system's snow line, where volatile compounds freeze, its migration inward could have delivered ice to the inner system. Impact studies suggest it might possess up to 5 times Earth's water content, creating crushing pressures in its hypothetical oceans. Yet without direct atmospheric measurements, we can't know if those waters are locked beneath ice shells or freely lapping against rocky shores. Future telescopes like the Habitable Worlds Observatory might detect glints of starlight reflecting off surface liquids, or analyze atmospheric chemistry for vapor plumes from geysers erupting through ice. What makes Kepler 6.2f so compelling isn't just its checklist of habitable traits, it's the way it mirrors Earth while remaining profoundly alien. A day here could last weeks if tidal forces have slowed its rotation, with sunrises that crawl across horizons like molasses. The weaker gravity might allow taller mountain ranges and deeper ocean trenches, sculpting landscapes that dwarf our Grand Canyons and Marianas. And if life exists, it could be thriving in ways we've barely imagined, perhaps around hydrothermal vents in lightless depths, or floating in global seas under skies streaked with perpetual twilight. Until we peer closer, this world remains a masterpiece of celestial ambiguity, a reminder that the most Earth-like planets might still be utterly strange. Ross 128b offers what Proxima Centauri b can't: a chance for life to thrive without constant stellar tantrums. Just 11 light-years away, this Earth-sized world orbits one of the calmest red dwarfs known, a star so placid it lacks the violent flares that typically sterilize nearby planets. Picture a planet bathed in perpetual maroon twilight, where the sun hangs motionless in the sky, its gentle glow barely 1% as bright as our own. Yet that faint light might be the key to Ross 128b's potential, a steady, undramatic rhythm that could allow an atmosphere to persist for billions of years. What sets this world apart is the remarkable tranquility of its host star. While Proxima Centauri bombards its planets with radiation bursts capable of stripping atmospheres within millennia, Ross 128 emits only subtle flickers, like comparing a roaring bonfire to a steady candle. This stability dramatically improves the odds that Ross 128b has held onto protective gases, perhaps even developing Earth-like air pressure over time. Climate models suggest that with a modest carbon dioxide atmosphere, surface temperatures could hover around -60 degrees Celsius, chilly by Earth standards but potentially habitable for extremophiles. Add a dash of methane or other greenhouse gases, and those numbers climb into liquid water territory. The planet's origins add another layer of intrigue. Unlike many tightly orbiting red dwarf worlds that likely formed farther out and migrated inward, Ross 128b might have arisen right where it is, sparing it the gravitational turmoil that could have boiled off early oceans. Its orbit, just 20 times closer to its star than Earth is to the Sun, suggests a relatively gentle evolutionary path. Spectroscopic studies hint at a metal-rich composition too, increasing the likelihood of a robust iron core that could generate a magnetic field, nature's best shield against even mild stellar winds. Future telescopes are already lining up to investigate. The upcoming extremely large telescopes Mid-Infrared LT Imager and Spectrograph METI's instrument aims to analyze Ross 128b's thermal emissions, hunting for the telltale warmth patterns of an atmosphere redistributing heat. Even more tantalizing is the possibility of detecting oxygen spikes, a potential biosignature if found alongside methane or other gases that shouldn't coexist without biological recycling. Unlike Proxima Centauri b's flare-scorched skies, Ross 128's calm radiation environment means any atmospheric oxygen would likely stem from photosynthesis rather than stellar radiation splitting water molecules. Yet mysteries remain. Tidal locking could leave one hemisphere eternally sunlit and the other in frozen darkness, though thick atmospheres might soften these extremes. The planet's mass, at least 1.3 times Earth's, implies stronger gravity that could concentrate gases into dense, insulating layers. Some scientists speculate about cryovolcanism, with icy geysers erupting through frozen crusts to replenish surface chemistry. Others envision vast subglacial oceans kept liquid by geothermal heat and tidal flexing from the star's gentle pull. Ross 128b represents a quiet revolution in exoplanet science, proof that not all red dwarf worlds are hellscapes. Its serene stellar environment offers something rare: time. Time for atmospheres to stabilize, for chemical reactions to build complexity, and perhaps for life to emerge without the constant reset button of stellar flares. As observation techniques improve, this unassuming world may deliver the most profound message of all, that the universe's gentlest corners could be its most hospitable. Gliese 581g was supposed to be the Holy Grail, the first exoplanet ever discovered in its star's habitable zone, a world where liquid water could exist on the surface. 20 light-years away in the constellation Libra, this tantalizing candidate sent shockwaves through the astronomy community when announced in 2010. A rocky planet roughly 3 times Earth's mass, orbiting its dim red dwarf star at just the right distance to avoid freezing or frying. The headlines wrote themselves: most Earth-like planet found. A best candidate for alien life, but within months Gliese 581g became something even more extraordinary, a cosmic ghost. The controversy began with the detection method. Unlike transiting planets that cross their star's face, Gliese 581g was found through radial velocity, measuring the subtle wobble its gravity induced in the host star. The signal was faint, buried in noisy data from the HARP spectrograph in Chile. One team, led by astronomer Stephen Vogt, extracted what they believed was a clear planetary signature. Another group analyzing the same dataset found only random stellar activity. The debate split the field. Was this a groundbreaking discovery or wishful thinking amplified by statistical noise? What makes Gliese 581g so contentious isn't just the science, it's the emotional stakes. For believers, this world represents a triumph of persistence. Vogg's team argued the planet's 37-day orbit matched predictions for habitable zone worlds around such stars, with temperatures potentially allowing liquid water if atmospheric conditions aligned. Climate models painted vivid scenarios: a tidally locked planet where thick air currents circulated heat from the scorching day side to the frigid night side, creating a narrow twilight belt of temperate conditions. Some scientists even speculated about photosynthesis adapted to the star's crimson light, with hypothetical vegetation appearing deep black to absorb every precious photon. Skeptics, however, saw a cautionary tale. The Gliese 581 system already hosted 4 confirmed planets, their gravitational interactions complicating the signal analysis. Critics pointed out that red dwarfs exhibit star spots, magnetic blemishes that rotate in and out of view, mimicking planetary tugs. When rival researchers re-examined the data with different statistical tools, Gliese 581g vanished like a mirage. The European team declared they couldn't confirm its existence, sparking a years-long back and forth that left the exoplanet in limbo, neither fully confirmed nor entirely dismissed. The intrigue deepened with time. Independent analyses in 2012 and 2014 alternately supported and refuted the planet's existence, turning Gliese 581g into a celestial Rorschach test. Much depended on how researchers filtered out stellar noise, a process requiring subjective choices that could unintentionally bake in assumptions. The planet's proponents argued their critics were overly conservative, potentially discarding real signals along with the noise. Meanwhile, the skeptics warned against the perils of premature celebration, noting that false positives could divert attention from genuine habitable worlds. Gliese 581g's legacy transcends the technical debate. It forced astronomers to confront the limits of detection methods, spurring refinements in how radial velocity data is processed. Future instruments like the Giant Magellan Telescope may settle the controversy by directly imaging the Gliese 581 system, hunting for the faint infrared glow of a planet that might or might not be there. Regardless of its physical reality, this disputed world taught us a profound lesson. In the search for alien Earths, even our tools can't always distinguish hope from fact. And that ambiguity, as much as any discovery, defines the frontier of exoplanet science. Kepler 1638b hides in plain sight, a world so similar to Earth in size that it blurs the line between exoplanet and mirror image. Orbiting a sun-like star 3,000 light-years away, this rocky marvel measures just 1.02 times Earth's diameter, making it one of the closest dimensional twins we've ever found beyond our solar system. But it's not just the tape measure that intrigues scientists. This planet's 259-day year traces a near-perfect circle within its star's habitable zone, basking in stellar radiation almost identical to what Earth receives. Picture a world where sunlight filters through familiar-looking clouds, where the rhythms of days and seasons might feel hauntingly recognizable to any human visitor. The star at the heart of this system holds the real key to longevity. Kepler 1638 isn't some tempestuous red dwarf prone to sterilizing flares. It's a near twin of our own sun, slightly smaller and cooler but remarkably stable. Spectral analysis reveals minimal stellar activity, suggesting this star has weathered its 7-billion-year lifespan without the violent mood swings that strip atmospheres from orbiting worlds. That stability is a gift to potential life. While Earth's biosphere needed 500 million years to emerge from primordial soup, Kepler 1638b has enjoyed uninterrupted eons for chemistry to experiment twice as long as Earth's entire evolutionary history to date. Water's presence hinges on a delicate interplay of factors. The planet's mass, estimated at 2 to 3 times Earth's, suggests enough gravity to retain oceans against stellar winds, yet not so much that it crushes all geological activity. Tectonics could still churn beneath its surface, recycling minerals and regulating atmospheric gases through volcanoes. Climate models paint divergent scenarios. Some simulations show a world with modest ice caps and sprawling temperate belts, where rain might fall on continental interiors. Others suggest a global ocean interrupted only by volcanic island chains, their coastlines scoured by tides amplified by the planet's stronger gravity. The absence of extreme temperature swings hints at a functioning carbon cycle, perhaps even plate tectonics quietly reshuffling continents over geological timescales. What sets Kepler 1638b apart isn't just its checklist of habitable traits, it's the profound implications of its maturity. At 7 billion years old, this planet predates our solar system by 2 billion years. If life arose here, it's had galactic epochs to evolve beyond our wildest imaginings. Intelligence emerging even 1% earlier than on Earth would mean civilizations with 650 million years of technological head start. The mind reels at what might have blossomed in that unimaginable span, species that mastered fusion power when Earth's continents were still barren rock, or civilizations that transcended biology entirely. Yet tantalizing mysteries remain. Current telescopes can't confirm if Kepler 1638b has retained its atmosphere against billions of years of stellar wind erosion. The James Webb Space Telescope might glimpse atmospheric hints during transits, but definitive answers await next-generation observatories like the Habitable Worlds Observatory. What we're glimpsing now is merely the opening paragraph of a story written across cosmic time, a world that holds up a mirror to Earth while remaining profoundly alien in its possibilities. Whether it's a living laboratory of ancient biology or a testament to nature's patience, Kepler 1638b challenges us to reconsider what's possible when planets are given the one ingredient life cherishes most: time. HD 85512b walks the tightrope between habitable and hostile, a super-Earth towing the line of its star's Goldilocks zone with a delicate dance of atmospheric balance. Orbiting an orange dwarf 36 light-years away in the constellation Vela, this world weighs in at 3.6 times Earth's mass, a gravitational anchor that could cling to a life-sustaining atmosphere if its clouds cooperate. Here's the twist: this planet skims the inner edge of the habitable zone, receiving just slightly more stellar radiation than Earth. Without climate regulation, its surface might simmer like a pressure cooker. But nature might have crafted a solution as elegant as it is alien, a perpetual veil of reflective clouds acting as a planetary thermostat. Picture a sky choked with dense, sulfur-laden clouds, their bright surfaces bouncing sunlight back into space before it can overheat the surface. Computer simulations suggest that with just 50% cloud cover, similar to Earth's average, HD 85512b could maintain comfortable temperatures despite its closer orbit. These wouldn't be the fluffy cumulus clouds we know, but perhaps a swirling global layer of sulfuric acid aerosols or crystalline compounds exotic to terrestrial meteorology. The planet's stronger gravity would compress these clouds into lower, denser decks, possibly creating a permanent overcast that bathes the surface in diffuse golden twilight. The star itself holds clues to this world's origins. HD 85512 boasts unusually high metallicity. Astronomers speak for its abundance of elements heavier than hydrogen and helium. This chemical richness likely provided ample raw material for planet building, explaining how such a massive rocky world formed so close to its star. Heavy elements like iron and silicon would have clumped together readily during the system's infancy, creating a planet with a dense iron core and potentially robust magnetic field. That last detail matters immensely. A strong magnetosphere could deflect stellar winds, preventing atmospheric erosion over billions of years, a critical advantage for habitability. Yet challenges persist. The planet's 7,500 million year age raises questions about geological activity. Without ongoing volcanism or plate tectonics to recycle atmospheric gases, HD 85512b might have exhausted the carbon dioxide needed to maintain greenhouse warming. Alternatively, if geothermal heat still simmers beneath its crust, it could fuel active geology that replenishes the air, perhaps even cryovolcanoes spewing water vapor instead of lava. The planet's faster orbit, completing a year in just 58 Earth days, also suggests tidal forces might stretch and squeeze its interior, generating friction heat that sustains subsurface oceans. What makes this world so compelling is its razor's edge existence. Too close to its star, it becomes a Venusian hellscape; too far, a frozen desert. But in that narrow margin of possibility, atmospheric dynamics could engineer a stable climate against all odds. Future telescopes like the Extremely Large Telescope could hunt for spectral signatures of water vapor or carbon dioxide gases that would signal active climate regulation. Even more tantalizing would be detecting sulfur compounds, evidence of those hypothesized reflective clouds. HD 85512b forces us to confront a profound truth. Habitability isn't just about location. It's about the intricate interplay of air, geology, and time, a recipe that, even on the brink of too hot, might still cook up conditions for life. Tau Ceti E stands as a cosmic paradox, a world that defies easy classification as either a scorched wasteland or a steamy Eden. Orbiting the Sun like Tau Ceti just 12 light-years away, this super-Earth finds itself at the center of heated debates about the very definition of habitable. Nearly 5 times more massive than our planet, Tau Ceti E likely sports an atmosphere thick enough to crush a submarine, yet that same dense shroud could be the key to its potential as a life-bearing world. Here's the twist: it skims the inner edge of its star's habitable zone, receiving about 60% more stellar radiation than Earth, a deluge of energy that might have triggered a runaway greenhouse effect. Yet some scientists speculate that beneath those swirling, pressurized clouds, conditions could mirror early Venus before its descent into hellish heat. The comparison to Venus isn't just convenient, it's hauntingly precise. Both planets share similar starting points, rocky worlds with substantial atmospheres, positioned near the inner boundary where liquid water might exist. Venus likely hosted shallow oceans for billions of years before succumbing to volcanic outgassing and solar intensity. Tau Ceti E could be following the same path, its fate hanging in the balance between two extremes. With a surface temperature potentially reaching 200 degrees Celsius, water would exist only as vapor, creating a steam bath atmosphere where lead would melt. But below those searing cloud decks, atmospheric pressure might allow for a strange sort of stability. At certain altitudes, temperatures and pressures could resemble Earth's tropics, raising the bizarre possibility of aerial ecosystems, microbial life, or even complex organisms floating in temperate layers, forever aloft in a global ocean of clouds. What makes Tau Ceti E so contentious is the star it circles. Unlike the red dwarfs dominating exoplanet discoveries, Tau Ceti is a G-type main sequence star almost identical to our Sun in size and temperature. This similarity forces astronomers to confront uncomfortable questions about our own solar system's history. If Tau Ceti E proves habitable despite its intense greenhouse effect, it suggests Venus might have remained life-friendly longer than we thought, or that Earth narrowly avoided a similar fate through luck or some forgotten geological quirk. The planet's thick atmosphere could even act as a time capsule, preserving chemical clues about how terrestrial worlds evolve when pushed to the thermal brink. Observational data adds fuel to the debate. Initial studies suggested Tau Ceti e might be a mini-Neptune with a deep hydrogen envelope, but more refined analyses lean toward a rocky composition with a carbon dioxide-dominated atmosphere. The James Webb Space Telescope could soon settle this by analyzing starlight filtering through its skies. A detection of water vapor would electrify astrobiologists, hinting at active hydrology despite the heat. Even more telling would be sulfur compounds, potential markers of ongoing volcanic activity replenishing the atmosphere, much like Venus's endless eruptions. The deeper lesson here lies in how Tau Ceti e challenges habitable zone models. Traditional calculations paint clear boundaries where liquid water can exist, but real atmospheres complicate this neat picture. A planet with 10 times Earth's atmospheric pressure might maintain liquid water at far higher temperatures, just as water boils at 120 degrees Celsius in a pressure cooker. Tau Ceti e forces us to expand our imagination, to consider that life might not need Earth-like conditions, just Earth-like opportunities. Whether it's extremophiles thriving in supercritical steam or aerial plankton drifting through eternal cloud banks, this world reminds us that the universe rarely fits into our tidy categories. Until we peer deeper into its churning skies, Tau Ceti e remains both a cautionary tale and an invitation, proof that the line between habitable and hostile is far thinner than we ever imagined. Kepler 1229b is the quiet achiever of potentially habitable worlds, a rocky planet so perfectly placed in its star's Goldilocks zone that it practically hums with potential. Discovered 2,700 light-years away in the constellation Cygnus, this Earth-sized world orbits its dim red dwarf star every 86 days, basking in just enough warmth to keep water liquid without boiling it away. Picture a landscape where the sun hangs low and crimson, casting long shadows across valleys that might cradle rivers or shallow seas. What makes this planet remarkable isn't just its Earth-like dimensions, it's the precision of its placement. Kepler 1229b receives about 70% of the stellar energy Earth gets from the Sun, putting it in a sweet spot where climate models predict stable temperatures could persist for billions of years. But location is only half the story. The planet's host star adds layers of complexity. Red dwarfs like Kepler 1229 are notorious for their fiery youth, often bombarding nearby planets with radiation that strips atmospheres bare. Yet this star shows surprising restraint. Its relatively calm demeanor suggests Kepler 1229b might have clung to a life-sustaining atmosphere despite the odds. Tidal locking likely keeps one hemisphere forever daylit and the other in perpetual night. But simulations hint that thick atmospheric circulation could spread warmth across the terminator line, creating a ribbon of temperate conditions where life might gain a foothold. The real wild card: water. If this world retained even a fraction of Earth's oceanic inventory during its formation, those liquids could now pool in subsurface reservoirs, shielded from stellar flares by layers of ice or rock. Studying Kepler 1229b pushes our technology to the breaking point. At nearly 3,000 light-years distant, it's 30 times farther than the famous TRAPPIST-1 system, so remote that even the James Webb Space Telescope struggles to analyze its atmosphere. The planet's dim red sun, emitting mostly infrared light, drowns out the faint whispers of molecules in its air. Current instruments can't distinguish between a hazy, Venus-like shroud or a clear, Earth-like sky. Future telescopes like the Habitable Worlds Observatory aim to change this, using advanced coronagraphs to block stellar glare and reveal the chemical fingerprints of water vapor or carbon dioxide. But until then, scientists rely on ingenious workarounds, studying similar, closer exoplanets to infer what this distant world might be hiding. The tantalizing truth about Kepler 1229b is that it represents both the promise and frustration of modern exoplanet research. Here we've found a world that checks every box for habitability, size, temperature, orbit, yet its sheer distance keeps its secrets locked away. It's a reminder that the universe dangles possibilities just beyond our grasp, challenging us to build ever better tools to reach them. For now, this enigmatic planet remains a smudge of data, a pixelated maybe in the cosmic dark. But in that uncertainty lies its power. Proof that the hunt for life isn't just about the worlds we can see clearly, but the mysteries that keep us reaching further. JJ3323b defies expectations by turning stellar proximity into an advantage, a super-Earth that rewrites the rules of where life might cling. Just 17 light-years away, this rocky giant orbits so close to its dim red dwarf host that it completes a full revolution in just 5 Earth days. Conventional wisdom would mark it as a scorched wasteland, yet JJ3323b's secret lies in its star's feeble glow. The planet receives similar stellar energy to Earth despite its tight orbit, creating a paradox where blistering proximity and mild temperatures coexist. Tidal forces dominate this world story. Locked in a gravitational embrace with its star, one hemisphere likely bakes under eternal crimson daylight while the other sinks into frozen darkness. But between these extremes, models suggest a tantalizing possibility. Atmospheric currents could ferry warmth across the terminator line, creating a ribbon of temperate twilight where liquid water might pool. The planet's thick air, pressurized by gravity 3 times stronger than Earth's, might act like a global heating system, redistributing energy through hurricane-scale winds. Imagine jet streams wider than continents, endlessly cycling warmth from day to night in a planetary attempt to balance the scales. Beneath the surface, another drama unfolds. JJ3323b's elliptical orbit triggers rhythmic gravitational squeezing, flexing its interior like a cosmic stress ball. This constant kneading could generate intense geothermal activity, subsurface magma oceans powering hydrothermal vents, or even volcanic plumes punching through icy shells. Earth's extremophiles thrive near such heat sources in lightless ocean depths, raising the prospect that similar ecosystems might persist here, shielded from the star's capricious flares. The planet's high metal content, suggested by its dense composition, could further fuel this underground furnace with radioactive decay, extending the lifespan of its geothermal potential. The star itself plays an unexpected role. JJ3323 is unusually ancient, nearly 10 billion years old, giving this system twice the age of our solar system to experiment with chemistry. While younger red dwarfs erupt with atmosphere-stripping flares, this aged star has mellowed into relative quiet, its sporadic outbursts now feeble compared to its violent youth. Any early atmosphere lost to stellar tantrums might have been replenished over eons by volcanic outgassing or comet impacts, creating a secondary chance for life to emerge. Detection challenges heighten the intrigue. Current telescopes struggle to analyze JJ3323b's atmosphere directly, but future instruments could hunt for thermal fingerprints of tidal heating, infrared glows along fault lines or volcanic hotspots. The presence of carbon dioxide or methane would signal active geology, while oxygen might hint at photosynthetic life exploiting the star's dim light through infrared-sensitive pigments. Some theorists even speculate about subterranean biospheres, where organisms tap into geothermal energy much like Earth's deep-sea vent communities. JJ3323b stands as a testament to nature's ingenuity, a world where seemingly hostile conditions might birth unexpected habitability. Its existence forces us to reconsider the boundaries of life's playground, proving that even in the unlikeliest corners, the universe finds a way. Whether it's through atmospheric engineering, geothermal refuge, or some hybrid of both, this super-Earth whispers that life's true limit isn't distance from a star, it's adaptability itself. Kepler 283c challenges our assumptions about where life might take root, a world perched in the habitable zone of a star so dim it barely flickers in the cosmic dark. Discovered 1,700 light-years away in the constellation Lyra, this exoplanet orbits its lukewarm sun every 93 days, receiving just enough warmth to tease the possibility of liquid water. But here's the catch: Kepler 283c isn't the Earth-like haven we might hope for. With a radius nearly 2 times Earth's, it occupies a murky middle ground between rocky super-Earths and gaseous mini-Neptunes, leaving scientists divided over its true nature. The star at the heart of this system holds the first clue to the planet's contradictions. Kepler 283 is a K-type dwarf, smaller and cooler than our Sun, emitting a faint orange glow that bathes its planets in gentle warmth. For a world like Kepler 283c, this means the habitable zone lies much closer than Earth's orbit, wrapping the planet in a gravitational embrace that could have profound consequences. Tidal forces might have slowed its rotation to a crawl, leaving one hemisphere perpetually sunlit and the other in endless night. Yet, unlike the violent flares of younger red dwarfs, this star's steady temperament raises the odds that Kepler 283c could cling to an atmosphere over billions of years, provided it started with one. What truly puzzles astronomers is the planet's composition. That inflated radius could signal 2 radically different futures. In one scenario, Kepler 283c is a waterlogged mega-Earth, its surface drowned beneath global oceans hundreds of miles deep, with pressures so intense that water forms exotic states like superfluid ice or hot, electrically conductive slurries. Alternatively, it might be a mini-Neptune, a world with a thin rocky core smothered under a shroud of hydrogen and helium, its skies swirling with methane and ammonia clouds. The distinction isn't just academic. If it's the former, microbial life might thrive near hydrothermal vents on the ocean floor. If it's the latter, any hope for surface biology evaporates beneath crushing atmospheric pressures. The James Webb Space Telescope could settle this debate by analyzing the planet's atmospheric spectrum during transits. A detection of hydrogen would confirm a gaseous envelope, while heavier molecules like carbon dioxide or water vapor might hint at a rocky world with a dense, steamy atmosphere. But Kepler 283c guards its secrets fiercely. Its dim star makes observations notoriously difficult, and current data offers only whispers where we crave shouts. What lingers is the tantalizing ambiguity of worlds like this. Kepler 283c forces us to confront the messy reality of habitability, a spectrum where even planets that check every orbital box might still fall short due to their size or chemistry. Yet in that uncertainty lies its fascination. Whether it's a water world with abyssal depths or a gassy enigma with no solid surface at all, this planet expands our understanding of where and how life might find a way. LP 899c isn't just another exoplanet, it's a breakthrough discovery that's rewriting the playbook on habitable worlds. Found orbiting a faint red dwarf star 100 light-years away, this super-Earth has astronomers buzzing for one simple reason. It might be the most promising candidate yet for atmospheric analysis. Picture a world 30% larger than Earth, blanketed by thick air that could shield oceans or lakes from the harsh realities of space. But what truly sets LP 899c apart is its star, a cool, unhurried dwarf that barely flickers compared to our Sun's brilliance, offering this planet something rare among red dwarf systems, a fighting chance at keeping its atmosphere intact. The secret lies in the numbers. While most habitable zone planets around red dwarfs orbit so close they're roasted by stellar flares, LP 899c enjoys a more relaxed 8.5-day year thanks to its star's subdued energy output. Surface temperatures could hover around 20 degrees Celsius with an Earth-like atmosphere comfortably in the liquid water range. But here's the twist: this world is almost certainly tidally locked, one side perpetually sunlit while the other drowns in eternal night. That might sound like a death sentence for habitability, but nature has surprises up its sleeve. A sufficiently dense atmosphere, say 2 to 3 times thicker than Earth's, could circulate heat efficiently enough to prevent the dark side from freezing solid. Imagine hurricane-scale winds endlessly ferrying warmth across the Terminator line, creating a ring of temperate real estate where life might find purchase. Then there's the star's remarkable calm. LP 899 emits minimal ultraviolet radiation compared to its red dwarf peers, a trait that drastically improves the odds of atmospheric survival over billions of years. While stars like Proxima Centauri shred planetary gases with routine flares, this gentle sun might have allowed LP 899c to hold onto its protective shroud since formation. Recent climate models suggest even more tantalizing possibilities. If the planet started with substantial water reserves, its strong gravity could have kept those molecules from escaping into space, leading to a global ocean capped by dense, swirling clouds. Alternatively, volcanic outgassing might have built a secondary carbon dioxide-dominated atmosphere, creating a greenhouse effect strong enough to maintain surface liquids without triggering runaway heating. The real excitement, however, centers on what comes next. LP 899c is a prime target for the James Webb Space Telescope's atmospheric studies. Its cool star emits mostly infrared light, reducing glare that normally drowns out planetary signals, a quirk that lets JWST instruments peer deeper into its skies than most exoplanets. Scientists are already planning to hunt for water vapor, carbon dioxide, and even methane, which in the right ratios could hint at geological or biological activity. A detection of ozone would be particularly electrifying, suggesting the presence of free oxygen produced by photosynthesis, but the planet's thick air presence challenges too. High-altitude hazes, like those shrouding Saturn's moon Titan, could obscure surface features, while powerful atmospheric circulation might mix biosignature gases beyond detectable thresholds. LP 899c forces us to confront an exhilarating truth. Habitability isn't just about where a planet orbits, but how its atmosphere engineers survival against cosmic odds. Whether it's a steamy water world with global cyclones or a volcanic landscape with pressure-cooked seas, this super-Earth represents the next frontier in our search for life, a place where even tidal locking can't extinguish nature's ingenuity. As telescopes turn toward this enigmatic world, every new observation promises to test our assumptions about what makes a planet truly alive. TOI 1452b shatters our understanding of water worlds, an exoplanet so drenched it might lack any dry land at all. Discovered 100 light-years away in the constellation Draco, this intriguing planet orbits a dim red dwarf star, its surface likely drowned beneath a global ocean hundreds of miles deep. Unlike Earth, where water covers 71% of the surface in relatively shallow basins, TOI 1452b's liquid envelope could constitute up to 30% of its entire mass. Picture an abyss where the very concept of shoreline doesn't exist, just endless crushing waves under a hazy alien sky. The discovery unfolded through a cosmic tag-team effort. NASA test satellite first spotted TOI 1452b as a periodic dip in its star's brightness, the telltale sign of a transiting world, but the real breakthrough came from ground-based observatories. Using the sensitive SPI-RU instrument on the Canada-France-Hawaii telescope, astronomers measured the planet's mass through subtle stellar wobbles, revealing a density so low it practically screams water world. At nearly 5 times Earth's mass but only 1.7 times its size, TOI 1452b's bulk must be something far lighter than rock, a composition pointing overwhelmingly toward H2O. What makes this planet extraordinary isn't just the volume of water, but its possible structure. Earth's oceans are mere puddles by comparison, averaging just 2.7 miles deep. TOI 1452b's oceans, pressed by gravity 2.6 times stronger than ours, could develop exotic layers unseen on our planet. Near the surface, familiar liquid water might transition into high-pressure ices like Ice 6 or Ice 7, crystalline forms that remain solid even at scorching temperatures due to immense compression. Deeper still, these ices might give way to a supersonic phase, where water molecules break apart into a bizarre slurry of oxygen lattices and floating hydrogen nuclei. The planet's star adds another layer of intrigue. TOI 1452 is part of a binary system, its faint red dwarf companion orbiting far enough away to avoid disrupting planetary stability. This stellar calm is crucial without violent flares or tidal disruptions. TOI 1452b's watery shroud might have persisted for billions of years, providing a steady environment for chemistry to experiment. Astrobiologists speculate about hydrothermal vents on any submerged seafloor, pumping minerals into dark waters where life could cluster, oblivious to the lack of skies above. Yet mysteries loom. Current telescopes can't confirm if TOI 1452b actually has an atmosphere, a critical factor for surface liquid stability. Water might instead exist under a thick hydrogen envelope like a planetary pressure cooker. The James Webb Space Telescope could soon change this, analyzing starlight filtered through the planet's skies during transits. A detection of water vapor would cement its aquatic nature, while ozone or methane might hint at more complex processes, geological or even biological, unfolding in those lightless depths. TOI 1452b forces us to rethink the very definition of a habitable world. While Earth balances land and sea, this planet presents an extreme where liquid becomes the dominant feature. Whether it's a lifeless pressure chamber or a cradle for subaqueous evolution, one thing is certain: it proves that water, the universal solvent, can shape planets in ways far stranger than we ever imagined. JJ1214b defies categorization, a cosmic chimera that blurs the line between gas giant and water world. 48 light-years away in the constellation Ophiuchus, this enigmatic mini-Neptune orbits its dim red dwarf star so closely that a full year passes in just 38 hours. Yet buried beneath its crushing hydrogen-helium shroud lies a tantalizing possibility, an interior ocean so vast it could drown Earth's surface 10 times over. This isn't just another gas-shrouded oddity, it's a laboratory for redefining where life might lurk in the universe. What makes JJ1214b extraordinary is its atmosphere's opacity. Unlike Jupiter's transparent hydrogen skies, this world's air is clogged with thick hazes, possibly water vapor or photochemical smog, that absorb starlight so efficiently they create a global pressure cooker. The Hubble Space Telescope's observations reveal an atmosphere so dense that it blocks virtually all light from penetrating to lower layers, leaving scientists to wonder what simmering secrets might hide beneath. Some models suggest temperatures at depth could reach 280 degrees Celsius, hot enough to melt lead, yet potentially permitting liquid water under the immense atmospheric pressure. Imagine a realm where water exists not as ice or vapor, but as a supercritical fluid, blurring the boundary between liquid and gas in perpetual thermodynamic limbo. The planet's composition reads like a cosmic recipe gone sideways, with 6.5 times Earth's mass packed into a sphere 2.7 times wider. JJ1214b's density points to staggering water content, perhaps 60% of its total bulk. Gravity here would crush a human instantly, yet that same force might sculpt the interior into fantastical layers. A steamy atmosphere grading into a global ocean, transitioning through exotic ices like Ice 7, a crystalline form that remains solid at blistering temperatures before finally reaching a rocky core. The parallels to Jupiter's moon Europa are striking, except JJ1214b's ocean isn't buried under miles of ice, but smothered under hundreds of miles of pressurized gas. Habitability here hinges on an audacious idea. that life could evolve in lightless, high-pressure depths, surviving entirely on chemical energy from hydrothermal vents or atmospheric convection. Earth's extremophiles prove organisms can thrive without sunlight near volcanic seafloor vents, suggesting JJ1214b's hypothetical ocean floor might harbor similar ecosystems. The challenge is atmospheric survival. Red dwarfs like JJ1214 are notorious for violent youth phases that strip away planetary gases. If this world retained enough hydrogen to shield its water from space, while not so much that it crushed all geological activity, it might have struck a precarious balance between preservation and dynamism. The James Webb Space Telescope has already begun probing JJ1214b's mysteries, analyzing infrared light filtered through its hazy skies during transits. Initial data hints at water vapor and possibly methane, though the thick haze complicates interpretations. Future missions could hunt for chemical disequilibrium, unexpected gas combinations like methane coexisting with oxygen that might betray biological activity. Even more telling would be thermal maps showing unusual heat distribution, potentially signaling geothermal hotspots feeding subsurface oceans. JJ1214b's true lesson is its defiance of habitability conventions. It forces us to abandon Earth-centric assumptions that life requires surface oceans, sunlight, or even clear boundaries between land, sea, and sky. In this swirling pressure chamber, biology might flourish in forms we've yet to imagine, thriving not despite the extreme conditions but because of them. Whether it's a sterile laboratory of exotic physics or a hidden cradle of life, this mini Neptune proves that the universe's creativity outpaces our narrow definitions, and that sometimes the most promising worlds are the ones that look nothing like home. Kepler 452b isn't just another exoplanet. It's the closest thing we've found to a mirror Earth in the cosmos. Orbiting a sun-like star 1,400 light-years away in the constellation Cygnus, this world completes the grand tour of our 25 alien worlds with a profound sense of cosmic déjà vu. Nearly identical in size to Earth at just 1.6 times its radius, Kepler 452b basks in the same Goldilocks conditions that nurtured life on our planet. Its 385-day year traces an orbit uncannily similar to ours, receiving just 10% more stellar energy, close enough that with the right atmospheric composition, its surface could mirror Earth's temperate climate. But what truly sets this world apart isn't the present, it's the past. 6 billion years old, Kepler 452b predates our solar system by nearly 2 billion years, giving it an almost unimaginable head start for evolution. Picture a planet where continents had 2 extra eons to drift, where photosynthesis, if it arose, could have been refining oxygen production since before Earth's crust cooled. The star it circles adds to the mystique. Kepler 452 is a G-type main sequence star almost chemically identical to our Sun, with matching temperatures and luminosity. This rare similarity means sunlight here wouldn't appear amber like under a red dwarf or pale under an orange one. It would feel, in color and warmth, like home. The implications stir the imagination. With twice Earth's geological lifespan, Kepler 452b could have hosted civilizations that rose and fell before multicellular life even began on our world. Or it might be a cautionary tale, a planet that squandered its head start, its oceans boiled away by an unchecked greenhouse effect as its sun slowly brightened with age. Current telescopes can't confirm surface conditions, but atmospheric models suggest 2 equally haunting scenarios. One paints a lush, mature biosphere where forests of black-leaved plants absorb every photon from an aging sun. The other shows a Venus-like hellscape, a warning of what Earth might become in another billion years. Kepler 452b's discovery in 2015 marked a turning point, proof that Earth wasn't some cosmic fluke, but one of countless planets orbiting sun-like stars in habitable zones. Future telescopes like the Habitable Worlds Observatory might one day analyze its atmosphere for biosignatures like oxygen or chlorophyll, But even as data remains scarce, this world holds up a mirror to humanity's deepest questions. Are we alone? Are we early? Or are we just one thread in a tapestry of life woven across billions of years? As we conclude our journey through 25 alien worlds, Kepler 452b stands as both endpoint and invitation, a reminder that the search for life isn't about finding other Earths, but understanding how rare or common our story truly is. Whether it's a thriving twin or a silent monument to time's passage, this world challenges us to keep looking up and to wonder what might be looking back. From the crimson skies of Proxima Centauri b to the crushing ocean depths of TOI 1452b, these 25 worlds have rewritten the cosmic rulebook on where life might exist. Each one defies expectations, whether it's Teegarden star b thriving under dim starlight, or JJ1214b hiding oceans beneath a smothering hydrogen shroud. They prove habitability isn't just about Earth-like conditions, but about nature's relentless ingenuity in exploiting every possible niche. Frozen moons could harbor subterranean seas, while tidally locked planets might nurture life in narrow twilight bands. Hycean worlds like K218b stretch the very definition of habitable, showing that life could flourish under pink hydrogen skies or in supercritical fluids we can barely imagine. The search for these worlds has transformed astronomy from speculation into hard science. Where we once guessed at planets around distant stars, we now measure their atmospheres, map their climates, and debate their potential for biology. Kepler 452b taught us that Earth twins might be common, while Wolf 1061c warned that even the harshest environments could hide habitable pockets. The TRAPPIST-1 system revealed how planetary neighborhoods might share the ingredients for life, and GJ667cc challenged our assumptions about stability in chaotic triple-star systems. Every discovery, from the controversial Gliese 581g to the steamy promise of LP 899c, adds another piece to the puzzle, not just of where life exists, but how tenaciously it clings to existence across the cosmos. This isn't the end of the story, it's the opening chapter. Next-generation telescopes like the Habitable Worlds Observatory will peer deeper into these alien atmospheres, hunting for the chemical fingerprints of biology. Missions like Breakthrough Starshot could one day send probes sailing past Proxima Centauri b, snapping photos of crimson shores, and with thousands more exoplanets waiting to be found, each new catalog brings fresh surprises, worlds that make us gasp, rethink, and marvel at the universe's creativity. So stay curious. The greatest discoveries in this field aren't behind us, they're lurking in the next dataset, the next telescope image, the next aha moment when a scientist spots an anomaly that changes everything. Follow the breakthroughs, question the assumptions, and remember, every time we find a planet that shatters our expectations, we're not just exploring space, we're redefining what's possible. The universe has shown us 25 ways life might thrive beyond Earth. Tomorrow, it could reveal 25 more. The only limit is our willingness to keep looking up.